Maybe I should have taken a picture of these formulas we need to prove, but I didn't. So it just took a little time writing them up. Now G is defined as the sum with an additive character over all the x's, all the elements of some finite field. And I'll just try to solve these problems using the additive structure and not the actual definition of psi. This is not G. That's silly. It's chi of x. I just corrected. Chi of x times psi of x. There we go. And now when it's the trivial one, then it gives 1, the unit element for all x's non-zero, and chi trivial of naught vanishes. I believe the sum of all the values of the additive structure will vanish. FQ, now the additive structure, how can we prove they all vanish? That the sums. So we have a type of this of the additive group. And it will be some powers of p. I don't really know which, etc. powers of p. And then the generator here, let's call it A1, A2, they will map to some unit and then the whole group generated by the A's will map around the unit circle all the way around. So the sum of all these gives naught, as well as these. So an arbitrary sum will be the all the products, and then we can factorize that. So I think that is an argument that this sum vanishes, and psi of naught, of course, is 1. That means that it gives -1, which is what we should show. J chi1, chi2 is defined as the sum over all x's, chi1 of x, chi2 of 1 minus x. And when it's the trivial guy, then when x is naught, it vanishes, and when x is 1, the unit element, it vanishes. So there are just two places where it gives naught. That should be a sum sign. And there are q altogether, and we take 2 away, so that's really trivial. Now this one, well, we take it. And this gives 1 for all except x equals naught. So we have to sum over all of these guys except when x is naught. So that's the sum of all except y equals unity. And it's the same argument as above, that should give -1, and that's what it says. Good. Because chi of 1 is unity. All right, that was C. Now this guy, well, let's just do away with E before I think about that one. This is obvious because the definition is symmetric. So we just change variables, setting y equal to 1 minus x, then x is 1 minus y. So that's pretty obvious. So back to this guy. It's really strange adding the multiplicative and additive structures here. So maybe I should make an example to see what's cooking. And we take a very simple one, F3, well, 1 maps to omega, 2 to, oops, this is not a good one really. Let's take A5. So we need a generator of F5. I think we have 2 maps. Let's take the powers of 2. Two squared is 4. 8 minus 5, that's 3. 3 times 2 is 6. That's impossible. 2 times 4 is 8 modular. Well, I don't know. Let's take 3 instead. 3 squared gives 4. That gives 2, 3. Now what's cooking here? Oh, of course, the multiplicative structure. We have only 4 elements, so 2 would be quite all right. Never mind. And if this one goes to I, the imaginative, this goes to -1, maps to -I, maps to unity. And then, so this was X here, and that was the generator to, I don't really know. Now, what am I doing here? This is our X values over which we sum. We have to take 1 out. So 3 and -2, that's 3 squared. So the product gives -1. 4 and 2, that gives I. Oops, we have to conjugate this guy. 3 and -2 conjugated, that's unity. 4 and -3 conjugated, that's -I. 2 and -1 conjugated, that's I. Oh! And 4 times -3 conjugated, that's I. I get the sum 1 plus I. We just do it one more time. So we have 1, 2, 3, 4. 1 maps to unity. Two maps to, let's say it maps to I. Then 2 squared maps to -1. And 2 times 4 gives 3. That maps to -I. Right. And now we also take 1 minus x gives naught. Oops. I messed that up here. And 1 minus 2 gives 4. 1 minus 3 gives -2, that's 3. 1 minus 4 gives -3, that's 2. So chi of 1 minus x conjugated, naught gives naught, 4 maps to 1, 3 maps to -I, that gives I, 2 maps to I, that gives -I, and then the products, naught I -1 I. So now the sum gives -1 plus 2I. And according to the theorem, it should give +1. It seemed 4 gave -1 here. So that should be -1. So it's -I. So it gives -1. I times -I gives plus unity. So it's +1. And chi of 4 is -1. So what's special about this guy? I have no idea how to do this, so it's time for a break. I just got an idea. I have erased my example, which didn't lead to anything for once. This is the inverse of chi. And of course we must take away x equals the unit element. And then I just got this idea. So let's change variable and solve it in the field. And now we get, of course, x equals y divided by 1 plus y, provided y is different from minus 1. So, can this give minus 1? Then 1 plus x equals x. That's impossible. So, when we here take x distinct from 0, we get all values except minus 1. And the sum of all of them vanishes, so it's just equal to minus chi of minus 1. So it's just a question of getting the right idea. And for once, I learned absolutely nothing from an example. All right, that was the first part. Part 2, I'll just make another break and then write down the formulas. Here we are. This might be something like the same. And I believe this will follow from the one above, but let's check it out. First, the definition of G. Oops, yeah, that was not G. I did that the last time as well. Chi of x, psi of x, chi bar of y, psi of y. So first, these two guys, that gives chi of x divided by y. and then these give psi of x plus y. So it's time to change variables apparently. Or maybe some make distinct sums. If we sum so that x plus y runs through all the values of the field, then what can the fraction give? So we make new variables. A equals x plus y and b x divided by y. And here, of course, y is distinct from naught. Then this will vanish anyway. This will vanish anyway. So we must solve these for x and y. To see which values we get and how they're connected. We can put this into this equation. And that's if b is distinct from minus 1. And if b is minus 1, then they are opposite. So that holds if a is distinct from naught and b is distinct from minus 1. Oh, that's interesting, because that gives chi of minus 1. And a of naught is unity. So we take that out. Otherwise, we need to have x as well. X is b times I, so x equals times a. No, when doing this on screen while recording, I tend to lose the exact the prerequisites I do along the way. So we have to take these two values out, and they were equivalent to x divided by 1, giving minus 1, and this one and the sum being naught. Yeah, so this gives unity. Otherwise, do we have a one-to-one map? what I don't like here is that these guys, x and y, where we sum over fq, that means we have q squared values. Pairs. And down here we have q minus 1 squared values. And then if a and b, a vanishes and b is minus 1, that was equal to they having opposite signs. Oh, that's because x and y are distinct from naught, so we actually here only have q minus 1 squared pairs. That's weird, because when we take out here where x is equal to minus y, not being unity, that gives q minus 1. So I'm a little confused about the exact number I'm dealing with. And when we change variables to a and b, I wonder, what do we sum over? So I would like it to be distinct from naught, distinct from minus 1, chi of a, I didn't want to write this parenthesis. Psi of b. And since we sum separately, and then we have to take the sum with b being equal to minus 1, and what can a be then? That could be everything except naught. Oh, that's psi of a distinct from naught. So this gives q minus 1 possibilities. I'll just take a break where I solve this. And we've seen it before that I'm not really able to make such precise thinking while recording. So when it becomes very technical with various variables, then I get into problems. So I get into trouble when it gets technical with many variables. All right. It seems correct. The sum of all of these, not included, will vanish. So this is so when we miss the value giving 1, it's minus chi of minus 1. And now what do we get over here? Here we sum over these, and it's the same. The sum of all of these will vanish, except psi of so when we extend psi of minus 1, we get minus psi of minus 1. And then the sum of the chi's, oh, they will vanish. So it should be naught times psi of minus 1. So I don't get exactly what we should. We should get q times chi of minus 1. Yes, we should. Well, I think I have to think about it once again. So this is what I don't like. That this sum vanishes. Well, another break. I think I finally found the answer. Psi of the sums, psi of A and chi of B. Now we sum over all the guys, B distinct from minus 1. So that sum gives minus chi of minus 1. And A are all non-zero, so it gives minus 1. Altogether, Q chi of minus 1. My God, that was a stupid mistake. And it just goes to show how difficult it is to write on the screen using my tablet. That was that guy. And now we come to the last problem. What do we do there? I think we should multiply with the denominator on both sides and then try to see what we can do. Or maybe we should end with that. We'll see. This seems like the more complicated guy. Well. Of course, we need only have x distinct from naught and y distinct from naught. So we set a equal to x times y and b equal to y minus x times y. How about that map? A plus b equals y. So when dealing with the multiplicative group, I think this might give naught, might it not? Then x is 1. So there's a caveat there. What about that? Then b turns out to be naught. Well, that could happen, that's all right. And that means if b is naught, then x must be 1, so no problem. Then what is the values of b? Is there another value that b cannot attain? if xy lies in the multiplicative groups, then so does a. B does not necessarily. So I'd like to know if we can go the other way around. So we map x plus y to x times y, point x plus y. Is it 1-to-1? That's basically my question. And what is the range? Well, we must solve it for x and y. So let's go about doing that. So let's multiply this guy up here with x. And now b might be negative. So it's a plus b times x equals a. So a plus b must be non-vanishing. That's the point. So it's a map and then it maps into a point B. And now what was it? A plus B is non-vanishing. And A non-vanishing. So that's the, then we are home. We change variables, chi1 of A, chi2 of B, psi of A plus B, and it was A non-vanishing and A plus B non-vanishing. Well, we're almost home. That A need not vanish is irrelevant because chi of A then vanishes. But the sum here, that shouldn't have been. It should have been B not vanishing. I thought this would be very, very difficult, but it seems easy that I've just missed a little point. So we need to look at this where I want to go back and solve for x and y. And it bothers me that we get an extra term here, b equals naught, that just gives nothing here. It's like it goes out of the equation. So it's time for a break where I look at this and then find my error. Well, it seemed I was right. I just had to believe in myself and then we could go on with the show. So this sum is over b distinct from minus a. And that means that we can take the sum of all of them, which is g of chi2, and then subtract the value we get when it's minus a. This term, of course, gives g of chi1 g of chi2 minus, so it's key. Now what's happening here? Oh, didn't see that coming. We just write it out. Key 1 of A, chi 2 of A, chi 2 of minus 1, and then psi of naught. So this is the result we should get, minus. So we have to look at this sum and see if we can argue that it doesn't vanish. We take chi 2 of minus 1 outside the sum. So it's the sum of chi 1 chi 2 of A, and psi of naught gives unity. So we have to prove that this vanishes, and if chi 1 chi 2 equals the unit, or the what always gives 1, I don't know what we call that character, the trivial character, then the sum will give q minus 1 if it's any other character, then the sum will give naught. And that's why there was this condition in the, which I forgot to write up here. It only holds if chi 1 is not the same as the inverse of chi 2. And that's what ensures that this doesn't happen. So that solves problem 1.